In the last lecture, we introduced magnetism. We discussed terms like magnetic field intensity and magnetic field lines. Then we discussed the important topic of Earth's magnetism. We found that at any place on the Earth, the magnetic field at that point can be represented by three elements. We found that these three elements are not constant in time. Moreover, the Earth's magnetic field is quite weak, though it has very important effects. Today, we continue with magnetism. We shall see why some materials can be magnetized and some cannot be. Those which can be magnetized are known as magnetic materials. So, we start with atomic magnetic moment. We know that atom consists of nuclei and electrons. So, the electrons orbit around the nucleus, and an orbiting electron is equivalent to a current loop, which behaves like a dipole, and the magnetic moment of the dipole is given by this expression m equal to n times E h by 4 pi m, where n is the number of the orbit, h is Planck's constant, E is the charge of the electron, and m is the mass of the electron. This magnetic moment is due to the orbital motion of the electrons around the nucleus. In addition, electron has an intrinsic magnetic moment due to its spin. This we cannot easily explain. This is a quantum mechanical effect, but each electron has intrinsic magnetic moment. Each atom has therefore a net magnetic moment, part due to the orbiting electrons and part due to the intrinsic magnetic moment of the electrons. The magnitude of the magnetic moment of the atom depends on the detailed structure of the atom, how many electrons are there and how many orbits are there, and so on. For example, all completely filled orbitals carry no magnetic moment, because for every electron with spin s, there is one with spin minus s. That is, if spin is in this direction, we will find another electron which has spin in the opposite direction. Therefore, their magnetic moments are in the opposite direction and they cancel. And for every one going around clockwise, say electron going clockwise, there is one which goes around anti-clockwise. So, these magnetic moments are also cancelled. So, for filled orbits, the magnetic moments completely cancel. Of the unfilled orbits, if electrons are paired, that means if unfilled orbit also has two electrons, then the magnetic moment due to spin cancels out, and it leaves only the orbital magnetic moment. The net magnetic moment of each atom is oriented in random directions. Therefore, in the absence of any external field, a piece of matter has zero magnetic moment. I have shown here the magnetic moments which are randomly oriented. So, the net is 0. Here I show two electrons, one with spin up and the other with spin down. They cancel the intrinsic magnetic moments due to these electrons. So, on the basis of the behavior of their atomic momenta, materials have been classified as of the following types. 1. Diamagnetic materials. In these materials, the magnetic moments are only due to the orbitals. Remember that the orbitals have orbiting electrons have magnetic moments. Spin of the electron also gives the magnetic moment, but in this case in the diamagnetic materials the spins have cancelled out. So, only the orbital electrons are to be considered. The magnetic moment due to spins having cancelled out. When an external field is applied, the orbital magnetic moment tends to oppose the change in the magnetic flux. This is due to what is known as Lenz's law. We shall discuss this in the next lecture, and as a consequence align themselves in the direction opposite to that of the applied field. I will show you this. This is a diamagnetic material. You can see the magnetic field is in this direction and the magnetic moment of this piece is in the opposite direction. These are called diamagnetic materials. A diamagnetic material gets expelled from the magnetic field. You see, if you place a diamagnetic material and the magnetic field lines tend to avoid this. Such materials suffer weak repulsion when they are brought near a magnet. The examples are bismuth, copper, gold, water. Almost all materials possess diamagnetic property. You see, this is common to all. However, in many cases the spin magnetic moments are stronger and suppress their diamagnetic nature. So, in nature all materials are diamagnetic, but the magnetic moments due to the spins, they overpower and the substance becomes something else. What is something else? Paramagnetic materials. In materials in which the intrinsic magnetic moments are present because of unpaired electrons, I told you if the electrons are paired then their magnetic moment is 0. So, if there are unpaired electrons then the material can become paramagnetic material and are stronger than the orbital magnetic moment, and external magnetic field is able to magnetize them in the direction of the field. That is, in this case the orbital magnetic moments are weak. What is stronger is the spin magnetic moments, and they are directed in the direction of the field. Magnetic moment of such materials is directed along the field. These materials are called paramagnetic materials or paramagnetic substances. Such substances feel attracted by the magnetic fields. You see, you have a magnet and you have a paramagnetic material, it will be attracted, but very weakly. Magnetic field lines are drawn to these substances as shown here. If there are magnetic field lines and if you place a paramagnetic substance, then the field lines get attracted to this substance. However, magnetic strength is quite weak. Here is the paramagnetic substance. You can see this is magnetic moment of this in the direction of the magnetic field. On the other hand, for the diamagnetic material, the magnetic moment is opposite to that of the field. The most important materials are ferromagnetic materials. These materials act essentially in the same way as paramagnetic materials, but much more strongly. They get their strong magnetic properties from the existence of what are called magnetic domains. In each domain, the domain has a size from fraction of a millimeter to a few millimeters. In each domain, large number of atomic magnetic moments get aligned parallel or antiparallel due to very strong exchange forces between electrons. We cannot explain them here very in great detail because this is a quantum mechanical effect, and these strong forces within domains, they make the momenta of the atoms, they make them point in the same direction. So, in each domain you can see they point in the same direction. However, the overall effect in the absence of a field which is external is 0. When an outside field is applied as shown here, then all these domains, they start pointing in the direction of the field. Their momenta, they start pointing in the direction of the field. Not only this, you would also notice that these walls of the domains, they also change. They grow for those which are already in the direction of the field. So, you can see that this line was here, this has become, the wall has become here. So, the domains also expand, not only all the magnetic momenta, they point in the direction of the magnetic field, the domains also expand. The result is that the piece of a ferromagnetic substance becomes a very strong magnet, and magnetic field lines are strongly attracted to it. If these are the field lines and if you place a ferromagnetic material, then all the lines tend to crowd inside that material. This also gives an idea that if we wish to shield a region of space from magnetic fields, all that you need to do is to surround it by a ferromagnetic material. All the lines of magnetic field will crowd inside this ferromagnetic material, and the region inside would be free of the magnetic field. That is called magnetic shielding. Iron, which is in Latin called ferrum, is the most well known example of ferromagnetic materials. You can see ferromagnetic, the name is derived from ferrum, ferromagnetic materials. Cobalt and nickel are other examples of this behavior. Although the exchange forces responsible for this collective phenomena are very strong, yet thermal motions can thwart these forces above a certain temperature called Curie temperature. Below Curie temperature, the behavior is like a ferromagnetic material. Above the Curie temperature, this material becomes a paramagnetic material. In iron, the Curie temperature is 1043 Kelvin or 770 degrees Celsius. Above this temperature, ferromagnetic behavior of iron vanishes and is replaced by paramagnetic behavior. Ferromagnetism is not the only example of collective behavior. There are substances called anti-ferromagnetic substances, in which the exchange forces cause anti-alignment of the adjacent magnetic moments. You see, this is ferromagnetic alignment, this is anti-ferromagnetic alignment. You see, the alternate segments are aligned in the opposite directions, and the external field cannot produce any magnetization because these cancel each other, and the net magnetic moment of such a material is 0. We have already learnt that moving charges and currents are sources of magnetic fields. At any point, these fields are given by Ampere's law and Biot-Savart's law, which we have studied in previous lectures. We now learn that there are materials which can be magnetized, that is, they themselves contribute to the internal magnetic field. Suppose a piece of such material is placed in a magnetic field, say in a solenoid, then we have to distinguish between the fields produced by sources such as currents and that produced internally by the matter being magnetized. To do so, we introduce a new magnetic entity called magnetic field strength, denoted by H. You see what is happening? Earlier we have seen that magnetic field is given by Ampere's law or Biot-Savart's law. Now we find that there are materials which can be magnetized, that means they themselves become a source of magnetic field. Therefore, we have to introduce this new term called magnetic field strength. How do we do that? Let us write the magnetic field due to a solenoid, that is B equal to mu 0 n times I, where mu 0 is the permeability, n is the number of turns per unit length, and I is the current going through the solenoid. Then we can regard B as the product and Ni as the source. So, the source is designated as the magnetic field H. So, we call Ni H. Since n is the number of turns per unit length, the units of H are A by M. I is A amperes and n is per unit length. So, it is A by M. To distinguish from H, our familiar quantity B is redesignated as magnetic flux density or magnetic induction. This is measured in Tesla. From the above equation, the relation between B and H is H equal to B by mu 0. Now, if you introduce something, say magnetic material, a ferromagnetic material for example, in as the core of the solenoid, then this core is also magnetized and produces magnetization M. This also becomes a source of magnetic field intensity. So, instead of H equal to B by mu 0, we write H plus M equal to B by mu 0, where M is the magnetization, which is defined as the magnetic dipole moment acquired by or induced in the material per unit volume. This is also measured in amperes per meter. Like H and B, M is also a vector quantity. So, we can rewrite that equation B equal to mu 0 into H plus M. Further, M itself in most materials is proportional to H. Therefore, we can write M equal to chi H, where chi is called the magnetic susceptibility. It measures the response of the substance to the external magnetic field. So, if we do that, we get B equal to mu 0 into 1 plus chi times H, or simply B equal to mu H, where mu now becomes mu 0 into 1 plus chi. Mu is called the magnetic permeability of the material. Mu 0 is the magnetic permeability of vacuum or free space. Mu is the magnetic permeability of the material. Note that B equal to mu H, which we can write as B equal to mu by mu 0 times mu 0 H. Therefore, B is equal to mu by mu 0 we designate by mu r, relative permeability of the material. So, it is mu r into mu 0 into H. So, the permeability of the material is given by mu equal to mu r into mu 0, where mu r is the relative permeability. For diamagnetic materials, this chi, the susceptibility, is constant. It is negative because remember that diamagnetic materials they magnetize in the direction opposite to the magnetic field. Therefore, chi is constant, but negative, and here we show that the magnetization is proportional to H, and the slope is something like this. It is a negative slope. Paramagnetic materials, here chi is small, but positive. In this case, diamagnetic materials, chi was negative, small but negative. Here chi is again small but positive, and it varies with T as 1 by T. This has very important implications we shall study later. This varies as 1 by T, and the slope M is again proportional to H. The straight line shows that, and the slope is again equal to chi, the susceptibility. Now, let us see what happens to ferromagnetic materials when they are magnetized. As magnetic field H applied to a sample of ferromagnetic material increases, we increase H. Magnetization increases first linearly, and then of course, it saturates and becomes constant. When H decreases, when we decrease it, it does not come along the same curve. It now makes a separate curve, it comes back by a different route. That means, when H is 0, when you were increasing H, the magnetization goes like this. When we decrease H, it becomes 0. Even then, there is considerable magnetization left in the material. This magnetization is retained, and therefore, this is known as retentivity of the material. The magnitude of this on the y axis or the m axis is the retentivity of the material. This red line shows the retentivity of the material. Now, when you make H negative, then the curve follows this, and at some point the magnetization becomes 0. The field needed to make the magnetization 0 is called coercivity or the coercive force. You see, H is a force. So, H has to, when it is negative, it has to go a certain distance before M becomes 0, and this blue line is called coercivity of the material. So, this is retentivity. When H is 0, the material retains certain magnetization. To make the magnetization 0, we have to take H to the negative direction, and the amount needed to make M 0 is called the coercivity of the material. The phenomenon of magnetization lagging behind the magnetic field H as it is varied is called hysteresis. The curve is called hysteresis loop. You see, it lags. You see, it goes like this, and then when we bring H back, then it does not follow the same route. It does not become 0 when H is 0. So, lagging behind is called hysteresis, and this loop is called the hysteresis loop. Let us try to capture the physical picture. As the applied field increases, the domains in the ferromagnetic material are forced to rotate and align in its direction. At first, the process is quite rapid. All the domains as soon as the field is applied, all the domains very fast they start turning towards their magnetic moments start turning towards the magnetic field very rapidly. That accounts for the initial rapid rise in magnetization. This you can see initially it rises rapidly, and then of course it slows down because almost all the domains have already turned in the direction of the magnetic field. The work is done by the magnetic field in the solenoid that produce, not the magnetic field, but actually the current which flows in the solenoid. When the field starts decreasing, the domains do not come back. The domains do not come back because the material retains substantial magnetization. If they don't come back, then the work that was done by the magnetic field, all the current in the solenoid is retained by the substance. That means there is a loss of energy. When the field starts decreasing, the domains do not come back to the original state. The sample retains much of the magnetization. The inability of the domains to come back to their original state means that the work done in turning them is not recovered. You see, magnetic field was applied, then all the domains they turned, but now they don't come back. Their inability to come back is what is responsible for the loss of energy, and loss of energy is proportional to the area of the loop. Thinner the loop, smaller is the loss; broader the loop, larger is the loss of energy. To bring magnetization to 0, the field has to be applied in the opposite direction. We have seen that, and that is called the coercive force or coercivity. The phenomenon of hysteresis is very important for those who develop special materials for various uses in industry. Let us take a few examples. Suppose we want powerful electromagnets. We need a material whose permeability should be high, so that the magnetic induction of high strength can be produced. Remember, B equal to mu 0 H. So, or mu H, if mu is large, then for the same H, B is very large. At the same time, it should have small retentivity. Retentivity is the retained magnetization. This small, so that when you remove the magnetic field, the external magnetic field, the material comes back to the 0 magnetic moment. Both these will ensure rapid demagnetization and hysteresis loop of small area, and hence low loss of energy. So, we need a material which has high permeability, small retentivity and small coercivity. If small retentivity, small coercivity, then the loop is quite thin. So, smaller energy loss. Suppose we need to make strong magnets, permanent magnets. Obviously, the magnetization which is retained by the material must be high. So, it must have high retentivity and also high coercivity, so that it does not demagnetize easily. Cores of transformers and telephone diaphragms have to undergo repeated cycles of magnetization, because they subjected to the varying magnetic fields. So, for them we need low retentivity, so that it does not retain magnetism when current is switched off, and low hysteresis loss to save energy, and high permeability for stronger magnetic induction, which is confined to the core, and which also provides good flux linkages between the primary and the secondary coils by providing a path of low magnetic resistance. I have told you already that if we have one coil and another coil, then if we have a ferromagnetic material, then all the magnetic field lines tend to crowd inside the material, and therefore, it provides a much better path for low magnetic resistance. Another important property of ferromagnetic materials is the existence of temperature called Curie temperature. We have already discussed this, above which thermal motions can overcome the exchange forces, so that the existence of domains is no longer possible. Here I show you the Curie law or Curie temperature. Above the Curie temperature, for paramagnetic substances, you can see paramagnetic substances, paramagnetic, all through chi varies as 1 by T. For the ferromagnetic materials, only below the Curie temperature, this variation chi proportional to 1 by T is obtained. Above this law does not hold. So, chi proportional to 1 by T, known as Curie-Weiss law or Curie law, this T is known as Curie temperature. Below this, we have susceptibility going as inversely proportional to T. In the next lecture, we shall, as I promised, we shall discuss the Lenz's law and magnetic induction.